Okay, hello everyone. My name is Mario Guerra, and I'm here from Qualcomm Innovation Center to talk about VLIW and the MC layer. Okay, so if you've never heard of VLIW before, it stands for Very Long Instruction Word. The idea is it's an architecture designed to execute multiple instructions in parallel. And it's different from let's say a superscalar in that the instructions to be executed in parallel are statically scheduled by the compiler versus dynamically scheduled by the hardware. So I've got an example of a VLIW instruction packet for Hexagon up here. There's 4 operations, they're encoded in brackets, and the idea is that all these instructions get executed at once in parallel, okay? And so why do I care? Okay, well, the reason is because we've adapted LLVM MC as a standalone assembler for Hexagon. And Hexagon is a VLIW architecture with an optimizing assembler. The problem with that is that we found that there's very little native support for VLIW in the MC layer. It really seems to be designed to stream one MCInst at a time with minimal modifications to that MCInst. And we need awareness of a packet in order to do some of the optimizations that we need to do on a packet. Like, for example, we enforce instruction ordering within the packet, so we don't force the coder to do that. We'll actually do that for them. So we need to be able to shuffle the packet, and then we also look for opportunities to reduce code size by looking for operations that we can combine into a single 32-bit instruction. So we kind of squish those down. And furthermore, we also do some performance tweaking where we eliminate register dependencies by using what we call new value loads and stores. So we can load a value in a packet and then use that value in the same packet. And this is just an example down there that does a load of a half word, and then we store that newly loaded value out to another location in memory. And so what we did was we extended MCInst, we subclassed it, and we called it Hexagon MCInst, very original, I know. And we did that in order to capture the extra information that we needed for packet optimization. So we created a top-level Hexagon MCInst, and we set that up as an opcode equal bundle. And then for all of the instructions in a packet, we created separate Hexagon MCInst for those, and then we added those as MC operands to that top-level MCInst. So what we've got is this kind of a nested bundle, and this bundle passes through the MC layer as a single unit. And the nice thing is that the MC layer kind of treats it as a unit, and we do our packet optimization passes in specific Hexagon passes. And when it comes time to output the information to stream it as either assembly text or object code, we just unroll the bundle in Hexagon-specific subclasses of the streamers. So this is an example of what that looks like. So there's that packet again that I was just talking about, and this is what it would look like in the MC layer bundle. So we've got a top-level Hexagon MCInst that's declared as bundle, and then both of those instructions are declared as MC operand types, and you can see that that actual inst would be another Hexagon MCInst that then is declared as, in the first case, memh and then the relevant operands, and then the second case, memw and the relevant operands. So the basic design of MCInst turns out to be very well suited to VLIW. So we're very happy with how the bundling approach worked and representing instruction packets. It's very well suited. However, there's other aspects of the MC layer that aren't well suited to VLIW. For example, the parser assumes that a mnemonic is always the first token, which doesn't happen to be true for Hexagon, so it'd be really great to have more flexibility in mnemonic placement. Furthermore, the parser does not support the creation of packets. This is a big problem because we had to write a lot of custom code in order to get around the limitations of being able to build a packet. And so really what we need there is the ability to do several passes of token lexing before we invoke the streamer. And lastly, and most importantly, a lot of the information that we need in order to order instructions within a packet is lost in the lowering from MI to MC. So that's the primary reason that we subclassed MCInst. And I realize that's by design, but it does kind of make things problematic in some cases. And so subclassing actually raised other issues that I'm not even going to get into here, but it's just an issue. So really, we would like to see the support that's in there right now for VLIW, the MCInst, carried forward, and VLIW taken into consideration for future design of the MC layer. And that sums it all up. Thank you very much.